Thanks for joining us today. Today, uh, we're going to kick off our first guest speaker session of this year. We have Lukas Schaefer. Lukas is a postdoctoral research at Microsoft Research in Cambridge, UK, where he's a part of Katja Hoffman's team working on machine learning for video games. His work focuses on developing autonomous agents that enable novel experiences and tools in video games, with an emphasis on imitation learning approaches. Lukas holds a PhD and MSc in informatics from the University of Edinburgh and a BSc in computer science from Saarland University. His PhD research explored how to make deep reinforcement learning more efficient, with a particular focus on multi-agent systems requiring cooperation among multiple agents. Lukas is a co-author of the introductory textbook titled Multi-Agent Reinforcement Learning, Foundations and Modern Approaches, published by MIT Press. His work has appeared in leading ML conferences, including NeurIPS and AMAS, and he has been supported by German Academic Exchange Service, DAT, and the Stevenson Exchange Scholarship. The floor is all yours. Lukas, you can get started.
Thanks a lot for the kind introduction. Thanks a lot also for the invitation. Really nice to be here. Yeah, as Raul already mentioned, I'm a postdoc with MSR in Cambridge, UK, Cambridge. I always have to clarify for Microsoft, it's not in the US, around Boston. And yeah, I will be talking about kind of different things within decision-making in modern video games, kind of both trying to cover some imitation learning approaches as well as word modeling research that has happened in the team in the last couple of years. I'm going to try to aim to speak roughly like maybe 45 minutes or so, but I'm happy to also take some questions in between. I have some pauses in between and take some time later. So yeah, feel free to ask anytime. Okay, let's get started. So I already said at the beginning, at the moment, I'm a postdoc with MSR, working on decision-making in video games, but just so you have a bit of context of who's speaking, as Raul also mentioned, I did my PhD and MSc in Edinburgh, largely working on multi-agent reinforcement learning, did some internships at different places where we kind of looked at different things, for example, more real-world applications of multi-agent reinforcement learning, more foundational research at Huawei, and also an internship at Microsoft where I basically started kind of some of the work that I'm also going to be presenting. I would say kind of broadly overarching, the kind of things that I've been thinking about is, well, how can we efficiently learn decision-making? How can we learn to solve decision-making problems? And in this talk today, I will focus on my postdoc, so kind of the work that I've been doing with Microsoft Research specifically. Maybe only one thing that I wanted to mention up front, and Raul also briefly mentioned it. I co-authored a textbook on multi-agent reinforcement learning titled Multi-Agent Reinforcement Learning, Foundations and Modern Approaches. So if anyone's interested in kind of RL, multi-agent systems, game theory, and kind of how all these things intersect, I think this is a fantastic resource, and it is all freely available. So if you're interested at all in the topic, feel free to check it out on the webpage. But with that, let's actually get started talking about the research at Microsoft. I'm part of Katja Hoffman's team. She's kind of the person in the top left corner here, underneath the people-centric AI organization within MSR Cambridge, and we're kind of thinking about AI applications to enable new experiences for users as well as potential creators in the video game industry. This is kind of the current iteration of the team, but the work that I will be presenting throughout the talk has kind of also contributed to by many people who have kind of passed through the team in the last couple of years, as well as further collaborators within Microsoft as a whole organization. Microsoft Research in New York, Redmond, and other collaborators, engineers, and people at Xbox, for example. More just to bring the point home, I'm the one talking here, but really, this is not my work. This is really a big team effort of a bunch of fantastic people working on this research. So yeah, I'm just one small piece within a larger team here. Let's maybe think about at the beginning about why studying games and video games at all. I think there's a lot of kind of precedent, a lot of history studying games, but I think there are a couple of reasons why games are quite interesting to study for decision-making research. So you can go back to board games where people looked at chess, people looked at Go not even too long ago, kind of thinking about how to push the frontier of what AI models can do in terms of solving these complicated problems. And I think in the last decade or so, we started more and more push also towards the domain of video games, starting off with things like Atari, but then more and more going more complicated. And we see more and more research being done also on modern AAA video games that come with their own challenges and kind of, I would say decision-making challenges that we have to tackle and kind of pushing the frontier forward. So I would really make the case that I think games are a fantastic testbed to study and understand decision-making research, where our current limitations lie, and trying to push that frontier forward. And I think there are a couple of reasons what make them somewhat unique compared to other decision-making problems. First of all, I think there's a huge array of kind of variety in games. So no matter which part of decision-making you might be interested in, whether that is kind of partially observable decision-making or long horizon planning, really complicated decision-making action spaces, state spaces, whatever it is, you will find games that kind of match those criteria and that you can use and have already been built by other people. And now you can use it as a kind of a test benchmark for your system. But also, of course, there is an interest as well in video games as an entertainment industry. It's not just for kind of people playing it for fun, but there is kind of business behind it. It's one of the biggest entertainment industries in the world, significantly larger than kind of cinema, movie industry, music industry, notably so. The global revenue in 2025 was projected to be roughly $260 billion globally. So it's a huge business as well. And of course, a company like Microsoft is present in that business. So there is also a commercial interest in understanding these things. And I would say as well, and maybe not lastly even, is human players. We have kind of, as humans, an intrinsic interest in play and for fun and just playing these games. And I think that is actually quite meaningful for decision-making research, because it means that on one hand, you have potential access to data, but also you have a more intuitive understanding of these games. You get a sense of what are kind of skills that human players exhibit when they play those games, what are skills that maybe only highly proficient players exhibit in those games. And you can start comparing that to how an AI system might learn, potentially even asking different questions than how do we solve the game or play optimally, but rather how can we play like a human, which I think in many cases can be desirable for various purposes. So that kind of to kind of hit the ground and build up kind of the motivation as to why we're doing this type of research. There is commercial interest, certainly, but I think there are also other reasons to look at games for decision-making research. Now, most of you probably have seen some variation of a diagram like this before, where when we look at decision-making problems, we often think about kind of interactive decision-making challenges, sequential decision-making problems, where we have an AI agent that interacts with the environment, and they always kind of as input receive information about the state that the environment is in. This might be only partially observable, and then the agent will take some decision, some action, and that will then lead to a change in state of the environment that then again can be observed, and we can just kind of keep playing that game. And reinforcement learning, for example, you might also get additional reward from the environment at each step, kind of giving you feedback about how well you are doing or not. In the work that I will be talking about today, which is more data-driven, we actually don't rely on such reward signal being present. In the first part of the talk, I will focus on the agent side. Here I will talk about two different projects. One project that will kind of talk about visual encoders and thinking about, well, how should we actually encode the information, the visual information that we receive in video games to enable effective decision making. In the second part of the talk, I will talk a bit about kind of algorithmic innovation and how we can think about imitation learning to kind of better learn in the low data regime, specifically using techniques making use of inverse dynamics models. And on the last part of the talk, I will switch to the environment side and here talk about a project called WHAM on world and human action models, where we combine world models and imitation learning for kind of creative use cases in the video game industry. So let's get started with the first part of the talk. So for visual encoders for imitation learning, this is work that I presented last year at the AMAS conference at a workshop there, the ALA workshop. And in this work, effectively, we started off thinking about kind of general imitation learning pipelines in video games, so even more broadly, AI agents in video games. And when we looked at kind of prior work that people have done, both going back to things like Atari, but also more recently with like AlphaStar by DeepMind or the Sony AI work by, Sophia AI work by Sony AI, all of those really relied on game-specific engineering and infrastructure that was built. And that infrastructure was needed for various purposes. For example, to extract particular game state features that you might need as input to your model, or perhaps to extract some signal for a reward function to then train with reinforcement learning. And likewise as well, you needed such an interface whenever you wanted online interaction with the environment to facilitate that type of learning. But of course, from a scalability perspective, that is a bit of a concern. Like if you actually want to deploy things like this, now I would need to motivate the engineers for each game to maybe implement some APIs such that I can kind of query things, which might be feasible, but it's certainly a lot of overhead. So we kind of wondered, well, can we relax this dependency in this project? That's kind of how we started off. And then that motivated us to think about, well, there's already an interface to play video games, which is how humans play the video games, which is just, well, you observe the screen, the video game renders an image, you see that image, and you then react with inputs on your controller or your keyboard maps, whatever you use. So this is already existing. We don't have to implement anything for that. And kind of tapping an agent into that interface, as long as that's what we're doing, it's pretty straightforward. We just have to capture an image from the screen, and emulating a controller already exists software for open source that we don't even have to do ourselves. We can just leverage tools that people have already built. And then the game already knows how to understand that Xbox controller, for example. And secondly, because online training kind of typically requires some type of engineering around the game, we ended up kind of pivoting away from online learning like RL and more towards offline imitation learning approaches. More specifically, in the project, we pivoted towards behavior cloning, kind of the most standard, I would say, imitation learning approach, where effectively you treat imitation learning as a supervised learning problem. So you have a data set of, for example, human gameplay in a video game, in our case, and then we just sample images of what the humans saw at a certain time in the trajectory, for example, and what action they took. And then we just feed that image to our model. In our case, we kind of compartmentalize it into a visual encoder that gives us some lower level representation of the image, and then the policy network that actually outputs the action. And then we can just compute a loss between the action outputted of our model and the human action, and backpropagate that to our system to train. For the policy in this case, we kept it completely standard and fixed. We, across the board, use a two-layer kind of LSTM network as our policy. And the main interest of our study was, well, what can we do with the visual encoder? And the idea here really was that, well, the computer vision community in the last 10, 15 years came up with more and more innovation, better and better models to kind of give us very generalist feature extractors for images, if you will. Can we make use of those models in video games? And if so, which ones should we be using? That really, to us, wasn't clear at all when we looked at the literature. And there was some indication in, for example, robotics that people have already done investigations in, where they found a lot of these kind of more pre-trained visual encoders to be quite effective in robotics. But robotics looks a lot like the real world. A lot of robotics domains are straight up like real world images, which is the majority of the training data of these encoders. Does that actually still work when you give them Minecraft, which looks totally different like the real world? That wasn't clear to us. So we wanted to investigate this more systematically, and that is kind of how we ended up with a more, let's say, benchmark evaluation comparison across different encoders. To do this, we kind of first scouted out the kind of literature of, well, what encoders are people using. And first we looked at kind of what encoders can retrain end-to-end from the behavior cloning loss. And here we looked at different architectures of ResNet's vision transformers, different sizes of the models, as well as different input image sizes. And as I said, those are trained completely from the behavior cloning loss. The only thing we consider is using image augmentations during training, potentially. And then the main thing that we were interested in is, let's find out which pre-trained encoders might be useful here. And here we looked at different families again. We look at language contrastive models in CLIP. We look at self-supervised pre-trained models in DynoV2. We look at classification supervised models trained on ImageNet and FocalNet. And we have the stable diffusion, the AE models trained with reconstruction of images. And for all those, we just take them off the shelf and plug them into our pipeline. We don't do any training. We specifically want to see how well do those models deal with the potentially slightly out of distribution data that is video game data and images, and just see how they go out of the box. You certainly can expect to gain some benefits if you do some further fine-tuning, but we have specifically looked at the frozen case. In this project, we evaluated in 3 different video games. We looked at Minecraft, and here a tree chop task where the agent kind of runs around Minecraft and has to chop a tree or destroy a tree and then collect the log that they get from it. Secondly, we look at a kind of aim training map in Counter-Strike where you can't move, but you kind of move your mouse to look around, and you have to aim at targets that run towards you. And lastly, we look at Minecraft Dungeons, kind of a 3D action RPG game where we look at one particular level in which we gathered some data and trained our model that was more seeing whether we can push it slightly beyond the existing data sets that we could find open source available. And in this talk, I will be focusing on the results in Minecraft Dungeons. The results otherwise in the other 2 games are fairly comparable in general trends, and you can see the full details in the paper. Now, not everyone might be familiar with the game, so I'm just going to show kind of a short video here where you can see kind of some gameplay where effectively you control the character in the middle. This is a bit sped up, where you kind of attack with your sword, you can shoot your bow, you can drink some healing potion, and you always have to kind of move forward in the level. Here, for example, we have to defeat a bunch of enemies for the gate to open, and then we can go through, kind of progressing a bit further, navigating across the stairs, and then we have some more enemies where we have to defeat them, and then we can get to the next zone, which is kind of as far as we kind of evaluated in our systems. This is like 1.5 minutes, 2 minutes or so of gameplay, depending on the gameplay to reach it. And here there's a bunch of different enemies that we have to defeat and then collect kind of a couple key resources that are pointed out with these markers. And effectively, we do this until the game either goes game over after you died a couple times, or after 5 minutes, in which case we also always stop the evaluation or the data collection. Now, when we visualize our results, what we do is we basically segment the level into different zones that we have to progress through. So as far to the right, the better, the further you go to the right. And on the y-axis, we have the percentage of trajectories that reach a certain part of the level. So basically, you want to stay high as long as possible and not dip down as sharply, meaning more trajectories got further into the level. And first, I will show some results for the end-to-end visual encoders with the ResNet models. Solid line is always trained with image augmentation, dashed line without image augmentation, and then the different colors are the different architectures. And what we see, I'm going to try to break it down step by step because it's a lot of lines and a lot of plots. First, we see that the solid line in the same color is always above the dashed line in the same color, meaning image augmentation always helped. Image augmentation always improved our performance in Minecraft Dungeons. It was the case in Minecraft as well. In CSGO, it was slightly mixed, but generally speaking, not too much of a shocker that image augmentation is probably a good idea if you don't have a massive data set, especially. And secondly, we found that actually visual encoders, in this case the ResNets, for example, with comparably small image input sizes of 128, 128, perform better or comparable to ones with larger image resolution. This wasn't super clear to us. So here you can see the orange one, for example, being above the green one, which is basically the same model, just trained with different image inputs. Again, this wasn't very clear to us that that would be the case, because at the end of the day, for a lot of these modern video games, you need to pay attention to fairly small, precise details sometimes to actually make reasonable decisions. And it seems like actually the models can do so from a fairly compressed starting point, which is nice for computational and training resource reasons, because, well, training on larger images is always going to be more costly. If you look at different architectures and the vision transformers, we effectively see the same trends. Again, we see solid line always above dashed line, the same color, so image augmentation consistently help. And also here, we see that the same architecture trained on 128 images in purple performs slightly better or comparable to the brown one that is the same architecture with bigger image resolution of 256. But now let's get to the pre-trained visual encoders. That was kind of the bit that we were most interested in. Can we find a pre-trained model that actually works well in video games? And if so, which one could it be? Here, same kind of method of evaluation. And we have these 4 different families of models with different line styles corresponding to the different size of model within that particular family. And the first thing that immediately sticks out is, well, the gray lines kind of go up and all the other ones drop down pretty quickly. And the gray ones correspond to DynaV2. So really meaning that the DynaV2 pre-trained visual encoders, all 3 sizes of them, significantly outperform all the other pre-trained models, which are performing quite poorly, actually. DynaV2 seems very, very strong in its performance. And if we now compare it relatively to what we saw on the last slide of the end-to-end trained model specifically trained on the task that we are looking at, we can actually see that the best DynaV2 model is performing even better than the best end-to-end model that we trained. So really meaning a model that we have never trained on this particular task and that would hypothesize has probably not seen any data of this particular task at all during its training. It's more generalist purpose model for vision encoding. It's performing better than a model that has been specifically trained on this one task that we're looking at. That was actually quite impressive to see. And of course, at a certain scale, you might expect that. But for the video game data that is slightly out of distribution, I would argue that wasn't obvious to us. And this video that I showed you before actually is in particular a rollout of that particular DynaV2 model playing the game. So this is actually the model that we trained that uses the embeddings out of the DynaV2 encoder. So as we've seen, we can actually get pretty strong performance in these video games with pre-trained visual encoders. Now, something else we were interested in is, well, what about the efficiency? Like, what is the computational cost, for example, of doing this? And, well, these pre-trained visual encoders are fairly large compared to the tiny end-to-end ones that we trained on the data specifically. So you might assume that training is quite costly. So, for example, the medium-sized DynaV2 that performed the best has roughly 80 million parameters. And that is certainly true. If you do it naively, it would be quite costly. But if you want to use them as is frozen, you can do better than that. If you have a fairly small data set, it is certainly worthwhile to just iterate through the data set, basically do a bunch of forward passes to compute the embeddings and cache the embeddings for all images in the data set. Because then during training, you can just load those cached embeddings and completely bypass the visual encoder and the images, which massively reduces the computational cost. And just to kind of illustrate the gains that you can get from this, if we look at just the Minecraft data set, and we just train for 2,500 training steps, which is, by the way, much less than we did in the final training runs for our paper. If we just look at the cost of DynaV2 training with and without pre-computation, without pre-computation for the largest DynaV2 model, it almost takes 5 hours to do this training. With pre-computation, it takes 4.5 minutes. This is on an A100. And we need 54 gigabytes of RAM with the largest DynaV2 model compared to just 2.5 minutes. So this is a massive reduction in computational cost. Massive. It's really like you need an A100 to train this versus I can do this on my laptop GPU. And of course, on my laptop GPU, it won't be as fast as my A100, but it's still faster than the A100 doing it without pre-computation, which is quite astonishing. And I think this is great news for the community, because it means, well, people have a starting point. If they want to do decision-making research in video games, you now have a starting point that will not just reasonably work, but also significantly reduce the cost of your training pipeline. So to conclude, for kind of end-to-end visual encoders, we found small image sizes to actually be sufficient, which nice to see as well. That also reduces the computational cost if you want to go that route. And we found that image augmentations reliably help, which is nice to confirm. But most excitingly, the pre-trained visual encoders, in particular DynaV2, enable strong performance that is competitive, if not superior, to the performance if you get from training on task-specific data. And you can significantly reduce the computational cost of training if you do so. So two things that we were quite excited about. If you're interested in more details, the paper is available in archive, and we also open sourced the code base sometime earlier last year, so you can check it out there as well. And I might just take a minute to pause here to see if there's any questions, any thoughts, because otherwise it might be a lot to digest all of it at once, and then asking questions about it, what happened 40 minutes back.
Are these expert demonstrations?
Yes. So in Counter-Strike and in Minecraft, we used available open source data sets from prior work from Tim Pierce that he did in Counter-Strike, where he basically collected high quality human gameplay. And for the Minecraft one, we used the VPT data set from OpenAI. And for the Minecraft Dungeons one, we collected data ourselves. But yeah, that was high quality human gameplay, I would say.
And
which was quite important. Like, I think if you have much more random, low quality data, then I don't think you can do reasonable performance with the amount of data that we had, which was just like less than an hour in 2 games and 8 hours in Minecraft Dungeons.
And also, why were you using behavior cloning method? I mean, there could be any better imitation learning methods, right?
So I think it depends always what we're doing. So in the offline imitation learning regime, so if you don't have the ability to interact with your environment and you don't have any rewards, so you can't do RL, I think BC is actually a pretty sensible choice. Like, there are other approaches, and I will talk about this actually in the second project. There are alternatives that I believe under at least many conditions can probably work better than BC. But BC, I think, is a very standard starting point, and it seems fairly reliable from our perspective. So I think if you have a sensible size of data, you can often get pretty good performance out of BC, and it's very easy to do. So that was kind of the main reason, to be honest.
Right. Yeah, Kevin.
Any other questions? Otherwise, I can move on. We can also ask more questions later.
Yeah.
Okay, then I might just continue. Then let's get to the second. So in the first project, we were kind of emphasizing kind of the visual encoder part and studying that component specifically for imitation learning in video games. But we're kind of focused specifically, as Roel also asked about, like the behavior cloning algorithm. It's very standard, very common, but it's obviously not the only thing you can do. And here specifically, we're going to look at kind of predictive inverse dynamics model approaches in a low data regime. So in offline imitation learning, as kind of done in the previous part of the talk, we used behavior cloning, which, well, as I described, it's just supervised learning training of the policy. You just feed a bunch of inputs in, and you regress on the action outputs or use some classification output if you have binary actions or something. And one alternative that kind of became more and more prominent in the last couple of years were predictive inverse dynamics models, where the policy in red now effectively is a inverse dynamics model that is not just conditioned on the current state and kind of like BC asks the question of, well, if I'm here, what action should I do? It's an inverse dynamics model that is conditioned on a representation of the current state and a representation of a future state. Basically asking, well, if I'm here and I know where I want to be, what is the action that gets me there? And this you can train very nicely from the same type of data as you have in BC, because, well, in the data, you know where you will be in the future because you already have seen the entire rollout. That's why it's in the training data. But when you then evaluate your model, obviously you don't know the grand truth future case steps ahead of time. So what we do then is we train a state predictor model that is effectively trying to forecast the future. Given some representation of the current state, it tries to predict a state case steps ahead of time that is a desirable state to be in. So this really also needs expert demonstrations to train this particular state predictor. The inverse dynamics model you can actually train from more diverse data than just expert demonstrations. And people have done this. This is not something new we came up with. People have already done this. And for example, in the UniPy work, they showed this to significantly outperform different types of BC methods, I would argue. In this was in robotics domains. And there was also further follow-up work by other people with SEER and LDP, for example, where they used more transformer architectures and diffusion architectures and different approaches, but all kind of bottling down to the same base recipe, I would argue, of PIDM. And in all cases, they showed significant benefits over BC. And we saw this, we tried it as well in video games, and it did work reasonably well. And in some cases, it did work better than BC. But one thing we found kind of unsatisfying is, well, there's plenty of empirical evidence, people showing that this works, but no one seems to have an explanation as to why it works. And when can we actually expect it to work well? So we tried to understand this more fundamentally. So this work was more a mix of theory and empirical investigation, trying to understand what discriminates PIDM from BC, what allows PIDM to potentially work better than BC. So if we first go to the theory, very simply speaking, you could say PIDM is kind of a decomposition of BC. BC more or less implicitly has to think about where it wants to be in order to take its actions, but it's not actively modeling that function. PIDM basically tries to explicitly model what is a desirable future to be in and conditions the policy on that. So it's kind of a slightly different writing, if you will, of BC. And when you look at single point estimators for BC and IDM, so you just predict the expected action under your conditioning set of the state or the state and future state for PIDM, and you compare the expected prediction error that those would get on a supervised data set, then what you can show is under certain assumptions, the expected prediction error of BC minus the one of PIDM is greater or equal to 0, meaning BC always has a larger or equally large error on its predictions compared to PIDM. So PIDM effectively is always better under these assumptions. And we can further quantify what precisely makes up the difference of the two, which is this expected variance term. And you can kind of think of this expected variance term, I would argue, as, well, it's large whenever the future helps you to reduce uncertainty about your actions. So whenever the future conditioning that the IDM model gets is informative to discriminate between different actions, then that term will be large and PIDM will win more over BC because it has this future conditioning. But, and this is a big caveat, this theory is under the assumption of both optimal estimators and IDM actually having access to a true state predictor, so we have the ground truth future available to us to actually calculate this. So this is kind of what the benefits you can realize in theory if you have the optimal future predictor. So what happens if you don't have that, which is the typical case? Well, if you don't have the perfect state predictor, we're not lost. We can still derive theory to kind of compare the expected prediction error. So here now we're looking at the estimator for BC and PIDM. You don't have to read all the fine print. I'm going to try to walk you through piece by piece here. Effectively, when we're comparing, again, the expected prediction error of these two estimators, so again, the error of now non-optimal estimator of BC minus the expected prediction error of PIDM under the future coming from a state predictor that also needs to be trained on the same data that we have available. Those are kind of the setting that we're in now. We see that the difference between those expected prediction errors now comes down to 3 different terms. The first term is exactly the term we had on the last slide. It's just how much can the future help us to select actions effectively in PIDM. And this is a beneficial factor. We know this is greater or equal to 0, so it's beneficial for PIDM. It plays in PIDM's favor. Now we also have the other 2 terms. Delta is effectively the variance difference of our estimators. And we wouldn't expect that to be very different because the policy of IDM and BC have been trained on comparable data. Equally so with the last term, that is the bias term. But one critical bit, PIDM has an additional component besides the IDM policy that can introduce bias, and that is the state predictor. If you predict your future state and your future state prediction is completely off, your IDM policy will probably not give you a good action, right? So any bias, any error of your state predictor might harm your performance. So this beta term is effectively smaller or equal to 0. It can harm you whenever the state predictor is bad. So at the end of the day, PIDM kind of bottles down to a bias variance trade-off. You win some because you can exploit the kind of uncertainty of actions by having this future conditioning that might help you to make a better action decision. But at the same time, you introduce bias by the state predictor potentially not being perfect at predicting the future. So those are kind of the 2 things at play. And depending on which factor is larger or smaller, you will win or lose compared to BC. And we can actually perfectly prove that under certain assumptions, again, PIDM is guaranteed to be more sample efficient. So it needs less samples to reach the same error than BC whenever the variance term, so whatever we gain from this future variance conditioning, is greater or equal to what we lose from the bias. So again, kind of coming down to which effect is larger, and if the gains from the variance exploitation is bigger than what we lose in the bias of the state predictor, we will gain overall. So that's kind of a kind of summary of our theoretical insights in the work, looking both at kind of the expected prediction error for optimal and non-optimal estimators, as well as the kind of sample efficiency comparison. But how does this actually look in practice? Typically, ML theory doesn't always translate to empirical results. So how does this actually translate here? We also wanted to see how that works. And first, to be able to understand and kind of nicely analyze everything, we look at a comparably simple task where we have a 2D navigation task, which is fully observable. We control kind of this blue square in the top left corner here, where the action space is X and Y movement of our box. And we just look at, well, how good are we at reaching goals where the red squares are goal locations we have to reach in a particular order. So we can only reach a goal whenever we have reached already all previous goals and then go to that location. To make it a bit more interesting, we add stochasticity to the transition function. So there's some diversity in the data that is collected, as well as during rollouts. You kind of have to push against the noise that might push you slightly outside of course, which is just 0 mean Gaussian noise that we add at each step to the displacement of the agent. Under these settings, we collect 4 different data sets in 4 different tasks with different complexity. What you see here in blue are the traces of the human play when we collected our data sets. Now, for the models in BC and the IDM policy, we train small MLP networks. This is a pretty simple task. We are fully observable, small feature vector states. You don't need fancy models for this. And for PIDM, for the state predictor, we use kind of a horizon of 1. So we always predict the next state and condition the IDM policy on the next state. And for the state predictor, we don't actually train any neural network. What we do is we just use an instance-based learning approach, where when at rollout time we encounter a state, we look up in all our training trajectories that we trained on, what is the closest state to the state we currently see in our training data? And then we just say, well, whatever k steps ahead of that particular state we found to be closest in our training trajectory, whatever future we had then, we just use that as our goal state from the state predictor. And this is very cheaply to compute when you have small data sets, like in our case, and it's conceptually very simple. That's why we did it. We would think you can probably do better if you kind of throw fancy machine learning machinery at this, but here the proof point was more, let's keep it simple and actually easy to analyze. Now, when we actually now put this in our tasks, when we train these models offline on our data sets, on different sizes of data sets. So on the axis here, we have the number of trajectories from human data set in those tasks that the model has been trained on, anything between 1 trajectory for training or 50. And we train BC and PIDM. And then on the y-axis, we have the kind of ratio of goals reached at rollout time when we evaluate the model. And what we can see is an orange PIDM kind of goes up sharper, meaning for a lower amounts of training data, you get the same or better performance than BC. And kind of in the 50 trajectory for training regime, we see that both of them more or less converge to optimal performance. So in the limit, we would expect BC to do it, and it does. It's just that PIDM for less samples is already able to do very well. And we see the same picture kind of across the board in all different data sets and tasks. And the kind of performance gap, if you sample efficiency gap, if you look at how many samples does PIDM need less than BC to reach, for example, 90% performance, we see that we are needing 4x or 2x less samples, 3.5 on average. So significantly reducing the number of trajectories that we need to train on in order to get this performance. But that's kind of just the sample efficiency gains. Our theory talked about sample efficiency gains on a certain condition. We do see that being realized in this case. But our theory further predicted certain terms being critical for those gains. Can we also understand how they actually interplay with our experiments? And first, what we wanted to look at here is kind of this action uncertainty term and this delta that we popped up in our theory. And we wanted to try to understand how this impacts our learned policies. So first, we just compute, or let's say approximate, our delta quantity for different states in our data set. And then we can visualize this as a scatter plot. So kind of a darker color here is a state that has a high delta in our data set. This is purely a function of our data set. And a low, kind of very light colored dot is a state with a low delta. So we see, first of all, those are very much non-uniformly distributed. There is a wide spread of delta terms across states in our data set. And secondly, we see that there's kind of clusters of high delta states. And those are not just anywhere, but they're specifically around the goal locations that we have to reach in this particular task, which is no coincidence, because what this means is the human player kind of varied its actions more around those states, which is not too much of a surprise, because at the end of the day, those are the states where kind of precise control is the most critical. So the human kind of adjusts its actions depending on either prior mistakes of the action being taken by the human player or the noise kind of pushing it sideways. So really the takeaway is the states where the delta is high, which are precisely the states where our theory predicts PIDM to perform better than BC, corresponds to critical states around goals. So the gains are where we most need them, if you will. And if we visualize the IDM policy, we can query our IDM policy without the state predictor, just looking at the IDM policy for different states, for precisely those states where we computed the delta here for, and give it different possible future states all around it, and then see which in which direction is the action pointing. And what we see is in kind of the areas where we have high delta states in our data set, the IDM policy that we learn is learning precisely what we expect it to learn. It tells us with an action, which is just these arrows that we're plotting here, it points the action points from the current state to the future state we want to reach, which is kind of what we expect it to do. But whenever we look at states where the delta is low, we actually see that the IDM policy is basically ignoring the future state that we give it. It just looks at the current state, and based on the current state, basically gives us always almost the same action. Meaning the IDM policy is effectively saying, in this state, I don't even need to look at the future. Based on the data set that we had, I already know which action you want me to do here, so I'm just going to ignore whatever feature you show me and just point in that direction with my action. Which is, I would argue, desirable because it saves computational capacity for the states where you actually need it, and it doesn't attend to the future where it doesn't need to. So in those states with low delta, it kind of falls back to what BC would learn. Just look at the state, give me the action. But whenever it's beneficial to know the future, it actually attends to it, which is precisely what we see in the gains in our theory as well. Now, the other factor that our theory expects to be critical under non-optimal conditions is the state predictor. The state predictor might be wrong, and that might introduce bias. Can we also see the effect of that in our empirical experiments? So what we did here is we collected a new data set with an A-star planner instead of the human playing the game. So at each point in time, we just predict the action, or plan a plan to the next goal we have to reach, and take the action that the planner tells us to take. And what we would expect is, if we have a more narrow data distribution from the A-star planner, which we can also see in the visualization here, orange is the traces of the A-star planner, blue is the human gameplay. We see kind of the A-star being more narrow tubes of data, if you will. We would expect in those kind of data regime, we have more density of states. So we would expect our state predictor to be more accurate. Do we actually see that? And the answer is yes. Like if we actually visualize the accuracy of our state predictor, or the error of the state predictor here on the y-axis, and the number of training trajectories you have on the x-axis, we see that the human's trained state predictor, kind of the accuracy gets better as you have more training data, but it is always staying higher than the error that you reach when you train on the A-star planner data. And likewise, if we now put this all together and we also train an IDM model on this data, and we evaluate the PIDM approach trained on human versus planner data, we see that this lower error of the state predictor in the A-star data set also translates to even better sample efficiency. When now we get over 90% goals reached trained just on a single trajectory. And this is completely trained from scratch. There's no pre-training or anything going on. And this is all kind of in a 2D case, fairly simple tasks that allow us to nicely kind of analytically analyze everything. But, well, how does this actually do if you put it in more real-world environments? So we also put this in video games. I'm going to show you a video of gameplay of this PIDM model trained on a video game, Bleeding Edge, where we have kind of a task that we collect the data for. And I'm going to show it side by side with the human playing the same game, so it's the same task. And the model is trained on 30 human demonstrations. So on the left, you can see the human doing the task. On the right, you can see the PIDM model doing the task. I hope this comes through reasonably smoothly. And one additional point to note here is our model is running inference on a server in the US, while our game is actually rendered on an Xbox in South Korea. And we have to constantly communicate between the two. So effectively, there's a bunch of latency, random latency, that our PIDM model has to deal with during the rollout. So we actually see that it's quite robust to this kind of randomness that occurs as a result of this, and we're perfectly able to reproduce this trajectory with training trajectories of 30 training trajectories. So to summarize, in this project, we effectively studied these predictive inverse dynamics model approaches as an alternative to BC for offline imitation learning. We derived some theory that kind of now actually explains under which conditions you might expect PIDM to work well, and explains previous empirical results that it can be more sample efficient than BC. And we also further empirically validate what our theory also tells us in simple cases of 2D navigation problems, as well as more complicated real-world problems in video games. So that's the second project. And I think, yeah, as a note, there's nothing public or much public about this yet. And there will be a archive paper, a blog post, and code as well coming in the next weeks. So if you're interested in kind of this project and seeing more about it, keep your eyes open. I will post about it once it's out and you can access it very soon. And I think with that, I will go to the last project, and then we can take kind of questions for the rest at the end. I'm happy to stay a bit longer as well, if possible. So in this last part of the talk, I will be talking about world and human action models, WHAM, where we combine world models with imitation learning for video game kind of creative use cases. This is a project that was published in Nature early last year. And effectively, the project started with kind of a large-scale dataset collection, where we worked together with Ninja Theory, a video game studio within Microsoft, that had this title called Bleeding Edge, kind of a 4 versus 4 arena game, PvP with different players playing different characters. And we collected a large data set of roughly 7 years of human gameplay, roughly 1 billion images and actions being taken in that situation. And then we wanted to train a world model approach on it. And to kind of showcase the diversity in the data set, here are some videos. So you have all kinds of different characters, different effects going on. Each character has their own abilities, different maps and tasks. So it's quite diverse across the entire data set. And one of the ideas here was, well, can we kind of follow the more or less large language model recipe for scaling up models also in the space of kind of these decision-making models, in this case, a world model. So we start off first training an encoder model that takes in an image and gives us discrete tokenized representations of this with a VQV or VQGAN. And this is purely trained with reconstruction on the data set. This is the first part of training, effectively. Once we have trained this encoder, we train a kind of larger causal transformer model, 1.6 billion parameters total. And this model takes in as input kind of interleaved tokens that represent the encoded images and discrete representations of actions. And then we train it with next token prediction, basically in the same way as you would train an LLM. And what you get out of it is a model that effectively, when you look at the inputs and the outputs that it needs to generate, both combines a world model, basically conditioned on previous frames and actions, what is the next frame I would expect to see, and a imitation learning kind of behavior cloning representation of a human policy. Conditioned on previous frames and actions, what is the next action I should take? And because it's trained on human data and human gameplay specifically, it tries to emulate the distribution of human gameplay in the action distribution here. So once you have this model, what can you actually do with it? What we did is we went to kind of different creators in the video game industry, and we asked them, well, for different AI models that you might want to use in your workflows, what are criteria that you would need them to have in order for them to be useful? And 3 criteria that kind of consistently came up was, 1, consistency, where they wanted gameplay to be self-consistent, meaning the geometry of the world and stuff should not warp around, which, well, in many of these models does tend to happen. Secondly, they wanted the gameplay to generate from the model to be meaningfully diverse in the same way as the training data is diverse. And thirdly, they wanted objects and characters within the scene to persist. If you put them in the scene, they should stay in the scene. So we went and tried to evaluate all those components within our model. So what I'm showing first is videos for consistency, where at the top, I will show you first kind of on the left, ground truth gameplay in a video. And then you will see different checkpoints throughout training as the consistency improves. So here we feed the same initial frame and human actions into the model and ask the model to generate the remaining frames. And you can see in the earlier checkpoints, the geometry and the character often warps around, while on the very right-hand side, you can see the model actually keeping the environment very consistent and true to the ground truth data that we also see on the left side. And the same is true for other videos as well. This is a bit more chaotic because there's kind of comment going on, but we do see that the characters kind of remain in the scene and consistent. Other players in the scene are effectively part of the environment here in the modeling. So those will vary and be stochastic elements of the environment, if you will. So those will vary, but we see kind of the elements within a scene, as long as they're in the scene, they will stay consistent. Regarding diversity, we, for example, can look at the initial point in the level when you spawn. You kind of have different ways of entering the arena. And we see that in our data, if we kind of ask the model to generate the gameplay themselves, both the actions and the frames, we see that it kind of exhibits the diversity of the human play. Sometimes we go left, sometimes we go in the middle, sometimes we go right. And lastly, and I think this is actually the most exciting bit, is persistency. If we have some frame of the video game, what we can actually do is we can artificially introduce an object that wasn't actually there. We can Photoshop the frame to have, for example, here this object in the scene that the agent can interact with. And from this Photoshop frame, we start the model and ask it to generate actions and frames to kind of imagine human gameplay. And what you will see is the character controlled by the model here interacts with the object that we put in the scene that wasn't actually there. And the model accurately kind of models the physics and the transitions of the video game with this interaction of this object that we put there. And we can even go beyond. We can do this not just with static objects. We can go there and put enemies in the scene. And when we now ask the model to keep generating things, it will imagine how the enemy might behave, given the training data, and we'll see that the enemy starts attacking us, and we model all that dynamics accurately within the model. As I said, this is a paper that is out on Nature, so you can look at the paper, and we also open sourced part of this approach as well. So you can find different checkpoints on Hugging Face. You can find small snippets of the data set and Bleeding Edge that you can play with the model on Hugging Face. And we also open sourced a tool, the WHAM demonstrator, that you can use to kind of load the model and interact with it with the dummy data that we provide in a more meaningful way. Kind of going forward from that, just to conclude, the world model approach in this paper, we also analyzed the scalability of it. We find it to scale quite similarly to LLMs in both model and dataset size. And WHAM, we effectively combine kind of an imitation learning policy with a world model that allows us to kind of have this imagination of human gameplay without needing to even input any actions at all. The model can generate both. And in this particular project, we more focused on the use case for creators in the video game industry. Kind of remaining challenges here are, well, first of all, we needed a lot of data to make this work. And secondly, the frame generation of this model is comparably slow. And we already did some work to kind of push beyond that, kind of generating a real-time world model from much less data. There's a blog post up as well, sometime April last year that we published this. So you can look at this if you're interested. The TLDRs, we can actually get away with a fraction of the data and get a almost as high quality model out of it, as long as you have very targeted kind of data collection. There are some caveats. You lose some on the consistency and image quality side, but you can enable actually real-time interaction with a world model. And we actually made this available as a demo online, so you can play in Quake within a world model if you want. You can go and find this on Copilot Labs online. And I think with that, I will conclude. Yeah, some next steps may be interesting to hear. On the imitation learning side, the main thing we're interested in at the moment is kind of figuring out in this PIDM setting, where can we apply it and how can we potentially improve the state predictor side specifically, because it is so critical for the performance of this system. And on the world modeling side, we're kind of exploring alternative architectures and maybe different ways of introducing different modalities for controllability of the model. And also thinking along the lines of combining those two kind of families of approaches going forward. And with that, I will also open for any more questions. Sorry, I took a bit longer. I'm happy to stay another 10, 15 minutes or so if people have questions. I'm just reading the questions in the chat. Regarding the question of BC, BC fails to capture long-term dependencies in temporal context, right? So I wouldn't necessarily say so. So BC doesn't explicitly model the future, but in terms of long-term dependencies, if you're thinking about long context, I would say it's more a function of how do you instantiate your BC. So people have already done kind of large-scale scaling up of BC for different cases. I actually saw a new work coming out a couple of weeks ago from Elephant AI, doing large-scale BC in video games. And you can scale this up similarly as you do for world models, for LLMs, etc. And if with the right architecture, with the right approach, you can get pretty good kind of attending to the past and long-term reasoning out of it. So I wouldn't necessarily say that BC fails to do so. It's more, I think BC is a simple but maybe more brute force way of doing it. But at scale, it turns out to work pretty well, which I think is, I mean, equally true as for language models, etc. I think that's kind of the paradigm that we see there. Feel free to chip in and ask any questions verbally. Like, I'm happy to answer if there's more nuance that I'm missing. If not, I also see one question related to WHAM versus Diamond. Yeah, so I mean, Diamond, the work that LOI and Co did on Diamond actually also started in the team here at Microsoft. It's different in the initial architecture. So I think that's the first kind of distinguishing feature. And Diamond is diffusion-based image generation. WHAM was a pure autoregressive transformer, all discretized, quantized representations. So that's one immediate difference. And Diamond, from the very beginning, was aiming to get more to this real-time interaction. That was, I think, one of the critical kind of goals that they had, and were able to do so, impressively so. The kind of blog post that I mentioned that we put out last year in April is a different approach, more based on mask git, if you're familiar with that kind of masked transformer approach. Effectively, instead of predicting one token at a time, you predict many tokens at a time and then try to regress that way. And that significantly speeds up, and you can get also to real-time generation. So I would say those are probably most comparable rather than the OG WHAM, if you will. But yeah, otherwise still slightly different in their architecture, and I think that kind of implies what they're suffering from or what they're better at. We see these transformer models being pretty good, for example, at attending to specific things in the context. Diffusion models sometimes still, from my understanding, are harder to get to kind of pay attention to a large horizon in the past, but now there are also more hybrid approaches where people do kind of diffusion transformers and these kind of things, where I think that is getting better and better. A lot of the learnings, I would say, from video models at scale transfer over there to world models. It's quite similar, for my understanding, in terms of what you can gain there.
What was the context length that you were working with in your data from that video game?
So, sorry, in the WHAM world modeling approach?
Yeah.
In the world modeling approach, I want to say it was like 5,500 something tokens. But really what it came down to is, because each image is already a bunch of tokens, what it came down to is 10 images and action pairs in the context. So actually not very far back at all. And this is at 10 FPS, the data, as well as kind of what you do at rollout. So this is effectively looking 1 second back. So you won't get a lot of consistency for long temporal horizons. If you look away and you look back, it won't be there anymore. And so that's kind of not the type of consistency you do see. What we benefit a lot from here is that bleeding edge has static environments. So there's elements like the enemies or maybe spawn points of objectives that are random. So those, whenever you look away and look there again, will basically be resampled. But the geometry of the level is consistent because it is static in the data set. So that's very much different from, let's say, Minecraft. If you interact with Minecraft world models, it's kind of like a fever dream. You look away, you look back, and the geometry completely changed because the environment inherently is procedurally generated and random in the data.
Makes sense. Thanks.
Of course.
So for the bias and the variance that you had, did you also took into account some upper bound or the lower bound of uh, them in the slides that you had shown earlier?
So what we derived are just kind of expected prediction error approximation. So we don't do any recurrent bounds or anything of the kind where you might be able to derive a lower upper bound there. I think that's probably quite different machinery to derive that, but I think you could possibly think about it. We have briefly kind of started some direction in there, but it ended up being quite complicated pretty quickly. So we weren't able to do it, at least within the time so far. But there is probably more to be done there. This was more like starting the investigation into why do those models work. People see them work, but we don't really know why. And I think at least now we have a starting point of like, we have some understanding of why they can work and well, under which conditions. But I think there's certainly more to be done in terms of kind of more accurate bounds, for example, as one way of going forward with this.
Cool, cool. And the next part, like I would like to ask, is about like introducing noise in the sampling process, like those narrow like imitation learning policies that your your agent kind of learns based on the images and the wave videos. So does it follows them kind of to the like the letter, like in the narrow path that it tries to copy, or like do you kind of push it to introduce some kind of a noise, like instead of shooting this enemy, first shoot the enemy that is attacking you from the left, or like which is giving you the highest damage first, so kind of like that.
Sorry, you're talking about the second project with the PIDM?
Yeah.
So the question is about kind of how much
sampling,
randomness is there in
yeah.
the action sampling or in the data?
In the action sampling, in the final action sampling.
So in the action sampling, in this particular project, we modeled the navigation of the agent, which is kind of 4D continuous values to kind of rotate the camera and control the movement of the character. Those we completely model with MSE. We just continuous regress on it. So there's no sampling involved there. For the buttons that you have to press to, for example, attack enemies and things like that, we do model that as binary kind of categorical distribution, and there we sample from that distribution.
Okay. Cool. Yeah, so for that, like you have the choice to kind of shoot or like do some other sort of action to the direction it is pointing at. Your first person shooter is being pointed at. So like there is some sort of a noise being introduced. So like it's not completely trying to copy everything that or completely or trying to imitate what the like your initial data initial data had. It's trying to introduce some sort of a divergence that like you can model in.
I wouldn't say, I would say the model tries to introduce divergence. It is certainly trying to stay within the data distribution that it has seen during training, but it will never perfectly be able to do so, because the task in itself is inherently random. So there will be some deviation, and you will be able, or you will need to be able to deal with that and stay on track if you want to do it well. That being said, so the data that you collect here and the data you need for the task is absolutely critical. Like in our case, for example, we purposely collected, yes, 30 different trajectories, but we do try to stay on the same type of track. If you end up exhibiting very different behavior to do the same thing, you get a very multimodal distribution that you need to model. And then I think you will need to get slightly more sophisticated on the modeling side. You can do it, and people have done it before in robotics. So the LDP paper, for example, they look at using diffusion models for the state predictor as well as the policy. And if you use diffusion models, you can model more complex continuous distributions. So you're going to be fine. If you model it with MSE and half of your data goes left and half of your data goes right, you now just go in the middle, which is terrible, right? So you need to think about the data you have, and depending on that, kind of inform your modeling decisions. In our case, we intentionally kept the data simple such that we could keep the model simple, just to kind of keep everything a bit more straightforward. But depends on the problem you have whether you can do that.
True. Like in my early phase of my career, I was playing around with the Kala simulator and the donkey car simulators, and I was trying to do the same sort of imitation learning that you're doing nowadays with steroids. And the policy that my model was learning was too narrow to like the rounds or the paths that I took. So I was having initially the issues of trying to introduce noise so that it will kind of follow its own path with respect to every time going left or every time going right when I'm trying to dodge a particular obstacle. So yeah, that kind of thinking, that is why I'm asking these quick queries right now. Thanks for your awesome presentation and discussion.
Thanks for the question.
Thanks, Lucas. Can conclude the session now. Thanks. Thanks for the session.
Thanks a lot for the invitation again.